Good afternoon, everyone, and thank you for joining us for the Outdoor Art Club presentation, the latest and greatest news from the distant universe. I'm Kathleen Taylor, and I'm working today with Diane Wagner to bring you today's program. For those of you who are not familiar with the Outdoor Art Club, we're a nonprofit women's organization founded in 1902. The club engages in civic, cultural, and charitable work in our community. To give you an idea of a few of our past contributions, many years ago, the club sponsored and housed Mill Valley's first library. More recently, the club donated funds to provide landscaping for the Mill Valley Community Center. And in addition, the Outdoor Art Club has run a public speakers series for many years so that people like you have the opportunity to learn about topics as varied as how to design, plant, and maintain a vertical garden and the latest research and discovery in astrophysics. Before I turn this program over to today's program chair, please note that Zoom has two different functions, one for chat and another for Q&A. We won't be using the chat function today, but we will use Q&A for you to send questions to Xavier anytime during his presentation. He looks forward to answering them at the end of the program. At this time, I'd like to introduce Janice Prochaska. Janice is a member of the Outdoor Art Club and program chair for today's event. Hi, Janice.
Hello. Hello, everyone. First, I'd like to thank Barbara Derich, longtime Outdoor Art Club member and the original chair of this event today. Barbara arranged for Professor Prochaska 1.5 years ago to be with us. She has asked me to fill in for her today. So now, I would like to introduce Professor Prochaska. Xavier Prochaska is a trained physicist and astronomer by profession and now an enthusiast of the ocean. His research focuses on cosmology and the birth and evolution of galaxies like our own Milky Way. He also has a passion for applications of artificial intelligence. Xavier is a distinguished professor at the University of California, Santa Cruz, where he resides with his wife and the youngest of his 3 sons. The other 2 sons are students at UC Santa Barbara and Cal Polytech. Xavier travels frequently to Japan when there's no COVID. He holds a cross appointment at the University of Tokyo and the National Observatory of Japan. He's also my son. So to start off, Xavier, please describe to us your path to becoming an astrophysicist.
Good afternoon, Outdoor Art Club and other attendees. Nice to meet you all. So my path to becoming an astrophysicist is pretty typical of astrophysicists, insofar as you can say anything is typical of being an astrophysicist, with perhaps one exception, in that I began in Rhode Island. Specifically Wakefield, Rhode Island. Here is an image from the property my parents used to own in Rhode Island before moving to Mill Valley. And pictured here are 2 of my sons. I used to look a fair bit like the older one here, with having very blonde hair, very white hair even. But like him, both of our hairs have gone old with time. And my path to astrophysics really started in the home here, where I recall staying up late reading a magazine known as Scientific American. My parents loved magazines, and I imagine either they or one of their friends gifted me a subscription to Scientific American. And I did what I could as a 7th or 8th grader, sometime around then, to understand the articles. It was beyond my grasp most of the time, but I do recall the ones that most excited me were the articles about cosmology, so the universe as a whole, and particle physics. And that planted the seed, I think, for what has become my career in astrophysics. The next major step, major milestone, or major push towards astrophysics came from this gentleman. That's not a mugshot. That is an image of my high school teacher, Crandall Dimmick. I will always refer to him as Mr. Dimmick. Here, this is grabbed from a webpage for the award he received for his teaching at my high school over his career. He was extremely dedicated, extremely passionate about teaching science. And he inspired myself and a number of my fellow classmates to enter the sciences, and many of us have gone on to careers in physics and beyond. I should also call out several of my math teachers who were also very influential in my education at that level, and really inspired me to become a physicist first and foremost. From high school, I went to Princeton University. I remember that I wanted to go to Princeton. It was my only choice. I don't remember why. Maybe my parents can remember. But I did, and I enjoyed it. It was great for me. Upon arrival, I met with my freshman advisor. He tried to talk me out of physics. He told me to become an architect. I guess I was too stubborn, and so indeed I maintained physics. And an education at Princeton in physics is very, what we say, theoretical, very equation heavy. You learn physics at the core. And I did, which meant I rarely touched equipment. Science is often experiment driven. It is experiment driven. But that was not the education you received at Princeton. And indeed, I had very little applicability in the real world. So the next step from leaving an undergraduate in physics almost always entails graduate school. And while I had a pretty clear path between high school and undergraduate, it was from here and actually the next several steps that you might say I was far less intentional in the choices I made, although looking back, they were all really quite good ones, but almost by accident. So when exploring PhD in physics, I went and discussed with several of the faculty, and this one in particular, David Wilkinson at Princeton. I walked into his office, and I will always remember him saying, "Go to UC San Diego and work with Art Wolf." I don't recall why. He came to that immediate conclusion, but amazingly, I followed exactly that advice, and it was an amazing, amazing advice indeed. So my next step towards becoming an astrophysicist was to move here to San Diego, not such a bad place to live, of course, where I pursued a PhD in physics at UC San Diego. As I said, part of the path I was on, the success is partly accidental. Part of that, big part of that really, was that shortly after I arrived at UC San Diego, these two telescopes, these are the Keck telescopes on the now defunct volcano in Hawaii known as Mauna Kea. These two telescopes had come into operation, and they were an amazing leap in technology, just leaps, way beyond anything that existed on the planet at the time. And so it gave me a tremendous leg up in my career. Just acquiring the data, publishing the data from that facility was enough to make a mark in the field. The other part of it was my mentor, the gentleman that David Wilkinson told me to go work with, Art Wolf, this wonderful man, born and raised in Queens, New York. He went to high school with Simon and Garfunkel, and then eventually wound up at UC San Diego. An amazing scientist, amazing human being. Loved to chat liberal politics. We did both discussed physics and politics at length, and then really used these telescopes on the left, the Keck telescopes, to do some pretty amazing science. It was during those days, although I remember spending maybe 2 days thinking about making a startup company for analyzing digital photos. After putting that to the side, it became clear I wanted to be an academic. And to become an astrophysicist and an academic, a real faculty member, the next step is to become a postdoc. It's very similar to being an intern as a doctor. You have your degree, you can practice your field, but you're not really a doctor. You're this somewhat in-between phase, or in our field, we call it a postdoc. And again, I took a path that I would have never predicted. I wound up at an observatory I'd never heard of. Art, my advisor, suggested I apply there, and I'm glad he did. The observatory is known as Carnegie Observatories. It was founded by a donation from Andrew Carnegie over 100 years ago, probably the late 1900s. On the left is a library from the main headquarters, which are in Pasadena. It's preserved, this library, and still used. I spent many hours in there poring over the literature. It's a wonderful place. And they used to, I still operate an observatory on Mount Wilson in Los Angeles, if you're familiar with that. But scientifically, most of the program, most of the research they pursue is now done in Chile. They purchased land on a mountain range in the desert of Chile. You can see that on the right. And the telescopes that I used for the most part when I was a scientist at Carnegie Observatories are these two in the background. And then they've since built these two additional telescopes, similar to the Keck telescopes, not quite as big, but very large telescopes for peering into the universe. From there, I became a scientist at UC Santa Cruz, a professor at UC Santa Cruz. Again, a step I would have never predicted. I'd never heard of UC Santa Cruz. I didn't know they did anything in the sciences, much less astronomy, but had the opportunity to visit one day, found it was a lovely place in the woods, on the coast, a very liberal part of our country, very much like where I grew up, but doing forefront astronomy as well. And I was drawn in immediately and thrilled to be hired there eventually. Part of the reason why is because it reunited me with these huge telescopes in Hawaii, the Keck telescopes. UC, all of University of California are partners. And so this gave me direct access to this game-changing facility. And it also gave me access to the Lick Observatory, which I imagine some of you have visited. This is on Mount Hamilton, just east of San Jose. And while the telescopes there are not of the same size of the Lick telescope, as the Keck telescope, they're still very powerful in their own right, and another scientific advantage of being here at UC Santa Cruz. And I decided it was also a nice place for my family, introduced by my mother, my wife, Gabrielle, here on the left, and 3 boys taken around Thanksgiving last year.
So Xavier, could you tell us what a typical workday is like for you?
You bet. So when I tell folks I'm a professor at UC, the first question I get is, what do you teach? And I often say, not much. It's true. That will not be one of my main activities that I'll describe to you as an astrophysicist. I tell them I'm an astronomer, and they often think of something like this, something really beautiful and romantic, perhaps, the notion of staring at the stars through a telescope. That's also, at this day and age, a misconception. This here pictured is Vera Rubin, one of our amazing scientists. She led discovery of what is known as dark matter. I'll mention later in the presentation. But I think even in her time, it was rare for folks to be doing the science by staring through an eyepiece. That's not how we collect our data today. And I have to admit, most of my time is sitting in front of a computer. This is an image I took yesterday. This is where I'm sitting right now. So for the 30 years I've been doing astrophysics, most of it is done with a keyboard, a mouse, and my screen. It is very much a computationally driven art and science. And so whether it's collecting the data, analyzing the data, writing about the data, communicating with colleagues, most of it is done through computing. Which isn't to say I don't use telescopes, because we do. Telescopes are at the forefront of the research. They're how we collect our data. This is a pretty confusing but really cool, I think, image of the main mirror. We call it the primary mirror of the Keck telescope, which I've shown you images of from the outside. And so see if you can wrap your head around it. I'm tracing with the red dot the outer part of the mirror. So you see hexagons. You should be able to see hexagons, especially in the upper half. This is a segmented telescope. So until this telescope was built, we would construct, fabricate one mirror, one big mirror out of glass. But this became infeasible. Like if you were to try to build a mirror that's 10 meters across, so from here all the way down to here's the bottom of the mirror, you can maybe figure that out by staring at the image. That's 10 meters across. You cannot build a single piece of glass that won't warp or be too hard to hold and too expensive. And so one of my colleagues, Jerry Nelson, designed what is called the segmented mirror. And so they're hexagons and then oriented together to make what is effectively one mirror. Again, that's 10 meters across. If there were a human in this tower, if they were standing up, they'd be about the size of the tower, maybe a little bit taller, to give you a sense of scale. And we use this mirror and the telescope to collect data, collect light from the edge of the universe. Now, I said I've emphasized we don't use an eyepiece. We don't stare through an eyepiece here with the Keck telescope. So you might be wondering, what do we do with the light we collect, or how do we handle it? And it's a fair analogy to think that instead of the eyepiece and putting our eyeball up to the eyepiece, we can take an iPhone or a phone or a camera and put it up to the eyepiece and collect the data into our little digital camera. Effectively, that's what we do. But our cameras are not handheld. They are roughly this size. You can see a human here, tremendous in size. One of the other instruments not pictured is larger than my office. And so within this box are a series of lenses and eventually a detector, not all that different than the detector in your iPhone or phone to collect the data on. So the light eventually makes it onto a detector. We take an image, very much like how you take photos of your friends. Now, again, for scale, I'll give you a sense of the endeavor of an astrophysicist. The telescope, probably in today's dollars, would cost about $100 million. And the instrument, the camera that we use to collect the data, take the images, take the photos, costs about $10 million. Give you a sense of scale. And then the price tag easily can go up from there, depending on how ambitious one is with their telescope or their camera. I'm a spectroscopist. I collect data from the universe, but I don't collect what you might think of as ordinary images. I collect spectra. And this prism here gives you a sense of what we're doing with our light before we collect it with the detector. In comes the light from, say, a star or a galaxy, and the prism, as you've probably been taught, spreads the light out into its many colors. You can hear the full rainbow: red, orange, green, blue, purple. And then we collect that light, the spread out light, with our detector, with our camera. And it looks like this. So when I say I collect images of the universe, these are the kind of images I collect. And if that looks like nothing but gobbledygook to you, that's fine. That's correct. Even for many astronomers that don't focus on spectroscopy, if I show an image like this, they'll be lost. Certainly a younger graduate student would have no idea what I'm talking about. Because when I say images of the sky, you're probably thinking of this. This is an image of a small patch of our sky with the Hubble Space Telescope, and you can see galaxies and you can see individual stars. But as I said, the prism has spread out the light, and it spread it out in the image I was just showing you vertically. So the object has been spread out up and down, just like in the prism, up and down. And so the galaxies and the stars here are the streaks of white light going up and down. That's my star or my galaxy. And it takes quite a bit of effort, quite a bit of computing to turn this pretty crazy looking image into what we finally study. And that is a spectrum. And we're always taught to never show a spectrum in a public talk. It's even dangerous to show a spectrum in a scientific talk, because for most of the unacquainted, they look like squiggly lines and not much else. That's fine. That is a spectrum. And you'll have to trust me that by analyzing these data, we can learn a tremendous amount about the universe. How much matter is out there, how it's moving, what it's made out of, how far away it is, and more. So really, when we say astrophysics, you pretty much have to take spectra and then analyze the physics of what's going on in your phenomena. 2 or 3 more slides here. Some of the other activities I do as a professor, of course, are mentoring. I've mentored many tens of students and postdocs in my career. Here are some of the more recent ones. I have university service. I am the representative of the NCAA, faculty representative of the NCAA program here at UC Santa Cruz. Here's some of the lead administrators. And last but not least, a big part of what I have done as an astronomer is travel. And that's related to the science. It's far too easy to talk to your own colleagues just around you or your own students and lose your way. By traveling around the world, and I often go to Japan for this, You learn new ideas, get different perspectives, and that's really key to being an astrophysicist.
So, Jason, what are some of your important discoveries?
If you were to ask my colleagues that question, I doubt you'd get a clear answer, or at the very least, you'd probably get several answers. And the reason is I tend to be more, it's fair to say my career has been more broad as a highlight, with a fair bit of depth, but I'm pretty well known for being broad in that I've worked on a number of things. And so I'm going to highlight a few different projects. In fact, if you go to a website that collects all the literature of astronomy and put my name in and ask, what do I work on? Then you'll see, indeed, I've got kind of 5 major areas here color-coded. And the words may not mean anything to you. That's okay. These are astronomy gobbledygook words. I'll give you a little bit of a translation. The orange here is galaxies, gas in galaxies. The red here is gas around galaxies. The purple is really bright gas shining around galaxies and beyond. The blue are gravitational wave sources, which I'll come back to. And the green are what we call fast radio bursts, which we don't even really know what those are. So I worked on a variety of topics. And as a result, I've worked with a lot of scientists, astronomers. This is the full set of all the people I've written a paper with. I don't know how many that totals. It's probably around 100. So it's a collaborative endeavor. And to be able to work on these 5 different areas of research, I've needed expertise and drawn upon it throughout my career. If from the high level, what I've worked on is the cosmic web. This is an image from a computer simulation. It's a visualization. It's not real data. Call it an artist's conception even if you prefer, but it's a computer simulation of our universe. So we now have the hubris to model our universe in a computer from start to today. And when we do that, this is the prediction for how our universe looks on really large scales. So to press upon you the size here, our galaxy, the Milky Way, would be a pretty small yellow blob, maybe the one next to the red dot here, something like that. That's the scale of a single galaxy, which of course for our human minds is huge in itself. But now we're talking about grand scales in the universe, and what you should come away with from this image is this notion of a web-like structure. So the threads of the web are where there's more matter, more stuff in our universe. And there are patches of the universe where there's very little stuff. We call it a void. And galaxies often group together. Sometimes in such an extreme way, we call it a cluster of galaxies, or maybe thousands of them within a pretty small area of the universe. And my research has focused, again, I don't have a single focus. It's touched on how gas exists within galaxies. So the orange blobs themselves. Around galaxies, picture a scale something like this around this galaxy. And then in between galaxies. And when I say in between galaxies now, I really mean the universe as a whole. And I'll highlight 3 papers we published. Let's see, all in Science and Nature, I think, yes, kind of premier journals for astronomy research, Science Magazine and Journal of Nature. The first one focused on pristine gas. So I've now zoomed into one of these threads of the cosmic web. Here at the center would be a galaxy, the white part, think galaxy like our own, although way back in time. And this study focused on how much of the universe has been polluted with metals. It's kind of a weird phrase, polluted with metals. Here, what you should be thinking is the periodic table. Here's the periodic table, you might remember it. Hydrogen up here and helium up here. Astronomers refer to most of the other elements in a very crude way. We call them metals. You could call them heavy elements if you prefer. These are elements you're familiar with: oxygen, gold, nickel, iron, scandium. Elements you're not so familiar with here at the bottom. Crazy things that we've only been able to make on Earth. And we have proof that most of these metals, most of these elements are produced in stars. The orange, the yellow, the blue, the green coding are different paths for making the metals in stars. And you can see pretty much all the elements of our periodic table were produced in stars, generally towards the death of the star, often in a big explosion, which is cool. And our study was really focusing on how much of the universe is polluted by that process, by the formation of metals. And to our surprise, we found a few patches that were really pristine, had no evidence of any enrichment whatsoever, but that most of the universe indeed has a sprinkling, at least a sprinkling of iron and oxygen and carbon. Another major discovery, this one from last year, which was caught by the New York Times, is on how galaxies form, galaxies like our own. So we're looking way back in time, pretty much 90% back in the age of the universe, which is still 1 billion years, but that's a short amount of time for we astronomers. And this study used a telescope or an observatory, set of telescopes in Chile. This is the ALMA telescope, ALMA observatory. These are radio dishes you might appreciate. And we needed this $1 billion facility to have the power and the technical capability to see these very young galaxies towards the edge of our universe. And the major discovery here was that the galaxy we studied in detail was very disk-like. So our galaxy is like a disk, think a quarter or a frisbee, if you like. Many galaxies are disk-like, but it was a surprise to find a galaxy this early on, this mature and this disk-like in our universe. And it ran contrary to many of the leading theories of how galaxies form, and it's been inspiring the scientists who do construct those theories to go back to the drawing board and see what was missing from their descriptions, their models for how we make galaxies. And the third one is related to the bigger scales, the full cosmic web as I described it, and it focused on finding what we call the missing matter. So there was a long-standing puzzle as to where the ordinary stuff, the elements in our periodic table, where was that material? We used all of our telescopes to the best of our abilities for the last 20 or even 30 years to detect material we know should be out there, yet couldn't see. And the novel approach that we adopted was to use this telescope. This is in Western Australia. It's also a radio telescope. And with it, we detected something called fast radio bursts. It's one of my main research thrusts these days. And this is a little technical, so if you don't get it, that's okay. What is really cool about fast radio bursts, and we don't really know what they are, is that their signal, when it travels through a vacuum, all the colors arrive at the same time. All the frequencies of light, all the wavelengths. If you go through a vacuum, it'll arrive at the same time. But if you run that same signal through a universe with matter, our universe has plenty of matter in it, then the longer wavelengths, which is redder light, arrives later. So the shorter wavelengths, the purple light, arrives first at the telescope, and then the bluer and the longer wavelength, And the amount of time it takes between when the first light arrives and the last light arrives actually lets us count up how much matter there is in the universe directly. And so that's the study we published last year to great fanfare using this radio telescope and fast radio bursts.
So now, what is exciting you in astronomy today?
So looking at the present, there are several fields which really capture my attention beyond even, well beyond my own research. One of them is pushing the study I described, that Wolf disks, the study of galaxies in the early universe, pushing it to the very limits, pushing it to as far back as when the first galaxies formed. And we have predictions of when that is. It's maybe when the universe was only 5% of its current age. But these are very small. They're the first three, very young galaxies, very small, just forming. They're very faint, and they're very far away. So that makes them very hard to detect. the colleague of mine pictured here, he's now faculty in Tokyo. His name's Akio Inoue. You're pictured at eating a meal at an all octopus restaurant somewhere in Tokyo. He's used the ALMA telescope, which I've mentioned previous. Here's another image of it in Chile. He's used this ALMA telescope to now detect the most distant galaxies that we humans have recorded. These are small, very nascent forming galaxies. They're not so exciting to look at, but they're super amazing in that we're really peering back to the beginning of time and the beginning of formation of our first stars and galaxies. And so this green blob here is an image he took with the ALMA telescope of this very young galaxy. A bit of a side note, but I'll mention it anyways. If you looked at many images of the sky, I imagine most of you haven't, but if you had, you'd be struck by how many yellow galaxies are here. In fact, we call them red, yellowish, orange, red. This is a cluster of galaxies. This is uncommon, very little. If you point your telescope randomly, you very rarely see a cluster of galaxies. And that's part of the experiment. This cluster lies in the foreground, closer to us, and this green galaxy, the very distant one, lies behind it. And the foreground has actually magnified it. The term we use is gravitational lensing or gravitational magnification. It's artificially, although it's real physics, made this background galaxy brighter than it would otherwise appear. And that's what led him to do the experiment as well. It wasn't just this billion-dollar telescope, but using this foreground cluster of galaxies as a means to make the background one brighter. So that's super cool. Gravitational waves are another field which is as hot as can be. You undoubtedly have seen articles written in the media. Here pictured is a black hole using Einstein's concept of gravity. And gravitational wave, a lot of the science is about studying black holes for now and for the next number of years to come. This is a black hole as pictured by Einstein, say. And here the space-time, as we call it, has been infinitely curved. That's crazy. And I think you can appreciate if you push anything close enough to that black hole, it'll fall into it and never escape. That's maybe the concept you're supposed to get from this diagram, this picture. That's one black hole. Now, if you have two black holes, or you can even use two neutron stars if you know what those are, and you collide them together, then Einstein also predicted that when the two objects got very close together and as they're colliding, as they're touching and merging, then you would produce gravitational waves. So ripples in the space-time of our universe, the fabric of our universe. Very powerful if you're close to these two black holes, and powerful enough as they travel across the universe to now be detected here on Earth. And that has been one of the major advances over the last few years in science. This is the telescope we use. It's two underground tubes, about 1 kilometer long each. One in the United States, there's one in Louisiana and one in the state of Washington. Inside the tubes are lasers, and I won't go into it any further than that, but you'll have to believe me, we use those lasers in this telescope to detect those gravitational waves and thereby study black holes. And these are the signals, actually. I won't dwell on them. They're a bit complicated. But the signal that we can detect here on Earth lasts just about 1/10 of a second. It's the little chirp we get of this merging black hole system. And third and last for the present, what excites me is applying artificial intelligence to the massive data sets we're collecting. So the telescopes astronomers have been building for the last few years are amazing in their own right. We put on these tremendous cameras, and now we can collect data at unprecedented levels, levels beyond which I wouldn't have even dreamed of when I started as a PhD. My PhD was on 20 galaxies. 10 years ago, we had recorded studies of 1 billion galaxies. Sorry, 1 million galaxies. And we're now designing instruments to go for 1 billion galaxies. And so that's more data than one PhD student can possibly analyze on their own. And so we're taking advantage of what came out of video gaming industry. This is a graphical processing unit, a GPU, designed first and foremost for computer gaming, but now applied throughout science and really throughout much of your world. If you've been fearful of AI taking over, you should be.
So my last question, Xavier, before we go to Q&A, is what discoveries should we look for in the future?
So yes, now as I peer into my crystal ball and think about where astronomy is headed, where I know it's headed, I'll probably go from the definitely going to happen to the more challenging, or maybe won't happen in my lifetime. What you will see, right, which is already happening, but you will see more and more activity as the days go by, is direct imaging of exoplanets. And here the term exoplanets means not ours, not the ones in our solar system, not Jupiter, not Neptune, but planets around stars nearby, but not our own. And the technology is just getting to the stage where we can do this in a big way. You probably have heard that astronomers have now detected thousands of exoplanets. That's true. We've detected them. But imaging them is much harder. The techniques we use to detect them, I won't go into, but they're not direct images. But now this is an image of a protoplanetary disk. Most of the orange here is dust in around a star. The star would be here at the center where there's looks like a black hole. But the star's been blocked out. It will lie here at the center, and there is a big disk of dust primarily, out of which planets are forming. And it's asserted that this is a nascent planet around this star. And then over here in the movie, you can see 3 planets orbiting, actually 4, orbiting a star. I put the word quotes around solar system here. This is a solar system. It's multiple planets in orbit around a star. The star is not at all like our sun. The planets are not much like our own planets, but the concept is otherwise similar. And looking out to about 10 years from now, there'll be the technology will be developed and put in and constructed such that we will be imaging all sorts of exoplanets. I hope now more speculative, but not so speculative, is to discover the true nature of dark matter. If you've heard of dark matter, great. If you haven't, okay. It's stuff like our periodic table, like the stuff we're made out of, but not the stuff we're made out of, not the periodic table. It's matter, but in a form that we don't fully understand. The real evidence for it came from astronomy. And that includes, this is called the gravitational lens. The blue light here is a distant galaxy. It should look like this little blob if you can make that out on your computer screen. But because it lies behind this other galaxy, the orange one, it's been distorted and it looks like a ring. And we use observation data like that to prove that much of the universe, most of the matter in the universe, is dark matter. And these days now, physicists are building experiments with billions of your tax dollars to try to detect it in our laboratories and get a real true sense of what this stuff is. I hope we get there soon. Another area of very active research with telescopes being built as I speak is exploring the dark ages. We love the last 3 slides are all dark. Sounds a bit gloomy. The dark ages, this is the first roughly 100 million years, maybe a couple 100 million years of the universe. And some of the science we're after is when did the very first star form? Before that, there were no stars, hence it was dark. And this transition from the dark ages to a universe with stars and galaxies is being pursued with radio telescopes like this. This one's in South Africa.
Wow.
and I believe, we'll expect to hear some pretty amazing results out of that in the years to come. And last, I would be remiss if I didn't mention dark energy, but it's a little embarrassing in that I have no idea what it is. The evidence for it is it comes from supernovae. That is what's pictured here on the left, the supernova remnant. So this is a star that exploded a while back in our own galaxy. Studying supernova has taught astronomers that the universe is not only expanding, but accelerating in its expansion. And we finger this weird stuff. We call it dark energy. This is as good a guess as what dark energy is anyway. It's some psychedelic artist impression. And whether we really make any sense of it in my career, I'm a little bit dubious about, but who knows? And that's it.
Okay, so one of the first questions we had is how similar or how different are the different galaxies? Is ours typical?
Great question. I'll answer the last part first. Yes, ours is pretty typical. There's a wide distribution in size and in mass and in brightness. Those all go together. And we lie not at the true middle, towards the brighter end, towards the more massive end, but there are many galaxies more massive than our Milky Way. And there are many, many, many galaxies less massive and smaller than our Milky Way, but we're pretty typical. As far as the diversity of galaxies, there are two main classes. One is our class. We call them spiral galaxies. Star-forming galaxies is another way we describe them. We are galaxies actively forming stars today. That means the color of our galaxy is pretty blue. And then there's a whole other set of galaxies, roughly another half, the other half, which are red and are not forming stars, and their shape is more elliptical. So the two main classes are blue spiral galaxies and red elliptical galaxies. And our Milky Way lies in the first, the blue spiral galaxies.
So another question, where do we stand with using spectroscopy to detect possible life in the atmospheres of exoplanets?
Excellent question. We're not there yet. And one of my colleagues who does this for his career is a bit pessimistic that we'll get there quickly. One of my other colleagues is establishing here at UC Santa Cruz an institute for astrobiology. And so a main activity of that institute is to think about what signatures will we detect as humans in our spectroscopy of planetary atmospheres that we could point to and say, aha, there's life on that planet. And it's challenging. As I said in my presentation, where we will be in the next 10 years is imaging planets and taking pictures of them. And that's a great first step. And shortly thereafter, we are taking spectra today. We'll take even better spectra. But I've been told to be pessimistic that we'll get to biosignatures on a 10-year scale, and maybe more of a 20 or 30-year time scale.
So what do you mean by the beginning of time? Is there a way to judge the age of our galaxy or others?
Great question. So let's separate galaxies from the universe. Of course, galaxies exist within the universe. We judge the age of our universe in a few ways. The most powerful is by looking at a radiation field, light, that we call the cosmic microwave background. And I mentioned very briefly at the start, David Wilkinson, the person who pushed me to UC San Diego. There's a telescope known as WMAP, and the W is Wilkinson, and that was built to measure light left over from the Big Bang. And there are signatures in that light. I won't go into any detail, but there are signatures in that light, that radiation, that let us estimate the age of the universe. And we put it at 14 billion years. That's precisely measured today. Ages of galaxies are more challenging. They're made of stars, and we can make estimates of stellar ages. We do that. And our own sun is 4 billion years old and expected to last for about another 4 billion years. There are older stars in our galaxy, more than 10 billion years old. But it's not easy to precisely age date them. So yeah, I'd say 10 billion years, you could tell me it's 11. I could tell you it's 9. It could even be 12. So we use stellar spectroscopy, the short answer, to estimate the ages of the stars. And since stars make up the galaxy, we use that to estimate the age of the galaxy. There are stars in our galaxy that are more than 10 billion years old. And so we estimate our galaxy to be roughly that age, 10 billion, 11 billion years old, something like that.
So here's an intriguing question. What are some of the things we have learned about ourselves by studying the universe?
One of the things that blows my mind, or continues to, or certainly did as a PhD student, and one of the projects my advisor was most interested in pursuing for about 10 years, was to study the laws of physics across the universe. So, throughout humankind, we've placed ourselves at the center of things. At one point, we were the center of the Earth until we learned the Earth was round. The center of the solar system, center of the galaxy, so on and so forth. So we've gained perspective about ourselves and our existence from astronomy. And then tying it a bit more into my own research, what we've been able to do with the Keck telescope in particular, amongst others, is to ask and answer how different are the laws of physics across the universe, right? There's no a priori, it doesn't have to be, that the experiments we do in our lab on Earth as humans, that the laws of physics have to behave the same way throughout the universe. You could construct one that's not the case, but to the best of our ability, when we test the laws of physics in other parts of the universe, we find it's very much the same. So from the high level, I learned humility. We are a small piece of what is a vast expanse, and in no obvious ways, aside from life so far, are different.
Could you tell us a little bit about why you are interested in the oceans now? I think it's your turning 50 thing.
No, middle age is supposed to be 40, isn't it? I got through that one. Midlife crisis, whatever it's called. I am brought there by three things. One, I grew up next to the ocean, and my first research project was in oceanography at the Graduate School of Oceanography at the University of Rhode Island, about 100 meters from where I was wed. So I've always had a passion for oceanography. Just, it was beat out by astrophysics. Number two, two of the results I showed you in the slides of my own results happened last year, coincidentally within a week of each other. Those were 20-year science projects. I've been working on them for decades. And while there's more work to be done, it's not, at age 50, I'm not so keen to start another 20-year project, at least not in astrophysics. And the third is the artificial intelligence. So we've been putting up satellites around Earth since the 70s, maybe even a bit before that, to take images of the Earth. And that's just accelerated. It has only continued to accelerate. So we have an amazing data set of the planet, much more complexity, much richer than what we can take of the universe. And so when it comes to the techniques of artificial intelligence, machine learning, as we call it as well, that data is much richer in many ways than astronomical data. If you think to the image I showed you of the sky from the Hubble Space Telescope, most of the universe is dark. There's no light. Then there's galaxies, and they're blobs. You can describe them with about three numbers: its position, its color, its size. it's not very rich. Whereas if I show you an image of, well, we all know, even just think about weather, the complexity of processes in the ocean are far more complex. And you can still capture data that can address that complexity.
Do you think that the global community of scientists cooperate well, or do politics get in the way?
I'll answer it first from astronomers, which I know well, or physicists. I know them quite well too. I don't know other fields so well. Astronomy was pretty international when I started, but it's a data-driven science. We collect, as I said, data with our telescopes. And in the early 90s, it was a very much of a have or have not. So as I said, I was lucky. I didn't think to go to UC San Diego because of the Keck telescopes, but my goodness, I'm glad I did. And so in those days, the haves were only a few, and we thrived, and the have-nots were jealous, not to the point of, mean and trying to, I don't know, infiltrate our telescopes or something crazy like that. But over the last several decades, most modern nations have access to large telescopes. And some of the projects have gotten so expensive that we've been absolutely forced to become collaborative at the international scale. So it's become much more of an international effort. And that's true of physics as well, for sure. The great colliders you hear about in Switzerland and elsewhere, the LIGO experiment I showed you for gravitational waves, those are teams of 1,000 international researchers. So politics, because it's international agreements, there's always politics involved in how you set up the funding and who gets the credit to some extent, or at least who gets to publish and what the rules are for that publishing. There's politics there, but it's not that hairy.
So here's a technical one. Why does red wavelength pass through matter more slowly?
Right. I'll start by saying this is true. This is true whenever light travels through a medium. You may have heard, well, you've probably been taught, the speed of light is a constant. That's true in a vacuum. So there's one speed. We give it the letter C for the speed of light. What is it? 186,000 miles per second in English units. But if the light travels through a medium, and that can include glass or a swimming pool, or in this case, the plasma of our universe, it travels at a slower speed. And that effect, it's called the retardation of the group velocity, depends on wavelength. It's actually pretty simple electromagnetism in physics. You can derive it as a freshman in your university if you're studying physics. And I have to leave it at that.
That was from a graduate physics student.
Very good.
So, once you gave a talk and said there's 3 important things you need to know about the universe. It's always expanding, and I'm forgetting what the other 2 items are.
I think I can guess. I'll give you my guess, which is it's isotropic, which by that we mean it's basically the same in all directions.
Mm-hmm.
I would have said that, and I probably said it's flat, which is amusing. The Earth is not flat. Hopefully you've got that straight by now. But the universe is flat. And here, when we say the word flat, we mean it follows a Euclidean geometry, which is the geometry we were all taught in grade school, high school, and it's the one that follows our human intuition. Up is one dimension, there's a second one, and the third is towards the screen. So X, Y, Z, with the axes all perpendicular to each other. That's a Euclidean geometry, and that's a flat universe. It could have been that the universe was spherical And so for that, you should think traveling along the surface of the Earth. You probably know we take great circles on airplanes. Those are not straight lines in a Euclidean sense. They are curved straight lines. And so those are the three things: flat, isotropic, and expanding. And two of them came from that microwave background radiation, studies of that. The expanding, we had good hints at from Hubble over 100 years ago now.
So if you were to teach someone who doesn't study physics to think like an astrophysicist, what would you say to them?
Teach someone to think like an astrophysicist. I guess I'd start with, you need to be empirical. So I've said it several times, I'll say it again, it's a data-driven science. Well, I said I'm going to spend quite a bit of my time now studying the ocean because it's complex and astronomy isn't. That's not entirely the case. The formation of a galaxy is complex. The real formation of a planet, the dynamics of an atmosphere, right? Those are complex processes. Complex enough that you cannot write down with pen and paper and equations how they work. And you still can't, even with our amazing computers, simulate from first principles how they work. So you have to be data-driven. And that's the mindset I would encourage someone to be in if they wanted to think like an astrophysicist. What is the data telling me? Not what's it's also super cool to have wild ideas, wild theories, and go out to try and test them. But at the end of the day, the data trumps all.
So one of our members was asking if you believe there are other universes.
Other universes? I'm agnostic. How's that for an answer? Data-driven, again. We have no data that suggests it, nor do we have proof evidence that says it's not the case. One of my colleagues down the hall here has written a number of papers on multiple universes, multi-universe models. So very serious scientists take that very seriously. But we don't have means of testing that very well with our telescopes. And so I can believe it if I wanted to, but it would be at best a guess.
Okay. Well, we're coming to the end of our time, Xavier, and I really want to thank you for sharing your work and your passions with us today. We really appreciate you taking the time with us and teaching us things that we didn't know anything about.
My pleasure.
So this is the last of 21 webinars the Outdoor Art Club has done for its 2020-2021 season of public speaker series. The Zoom team has been incredible in making this happen for all of us. And I want to thank them for doing what they have done to learn so much technology in such a short time to make things special for all of us. So look for us next in September. We're taking the summer off. And if you've missed some of our programs, go to our website, outdoorartclub.org/public webinars, and listen to the recorded ones that we have there. So we hope to see you again in the fall. Please visit us on our website to sign up for notices. Thank you, everyone.